Welcome to This Explainer. You know, if you've ever just stopped, looked up at the sky, and wondered about the exact mechanics keeping those massive metal structures cruising right through the clouds, well, you are in the perfect place. Today, we're going to break down a complete, detailed, and comprehensive overview covering the core principles of flight. We're going to take these complex physical concepts and break down the aerodynamics that literally make the impossible possible. Okay, let's dive right into this, because it all really starts with one fundamental mystery. How on earth does a ridiculously heavy machine actually defeat gravity? I mean, it feels totally counterintuitive, right? You've got millions of pounds of metal, passengers, and cargo seamlessly soaring thousands of feet in the air. But as you'll see, the answer absolutely isn't magic. It is pure, elegant engineering and physics working in perfect harmony. To get there, here's our quick roadmap for today. First, the magic of flight. Second, the four forces. Third, understanding and overcoming drag. And finally, the anatomy of airfoils. All right, starting with Section 1, the magic of flight. So our core objectives here are pretty foundational. We really want to lock down exactly how airplanes fly, get familiar with the environmental factors that can completely alter an aircraft's performance, and understand those basic flight principles. If we keep these main goals in mind, all the technical details we're about to cover are going to make a whole lot more sense. Moving right along to Section 2, the four forces. Okay, so whenever a plane is up in the air, it's essentially in a constant state of combat with the environment around it. There are four fundamental vectors at play here. You've got lift pointing up, weight pointing down, thrust pointing forward, and drag pointing backward. And these forces, they are actively working against each other in a literal, non-stop tug of war. And this brilliantly illustrates what happens when we scale that concept up to a full three-dimensional aircraft. You can see how those vectors intersect right through the center of gravity. Now, to really grasp how a pilot actually controls the plane, we have to break this massive 3D tug-of-war down into two completely separate battles that are happening simultaneously. The first battle is vertical. It's lift versus weight. Lift is that crucial upward force, passing over and under the wing that supports the airplane in the sky. Opposing it is weight, which is just the unyielding force of gravity constantly trying to pull the mass of the aircraft back down to Earth. Simply put, for a plane to even leave the ground, lift absolutely has to conquer weight. Then we have the second battle, which is entirely horizontal, thrust versus drag. Thrust is your forward power. It's what literally propels the airplane through the air, driven directly by the amount of engine power the pilot uses. But opposing that thrust is our old friend, drag. Drag is a stubborn, backward, retarding force that actively limits the speed of the airplane. Basically, you can't get speed without fighting drag. Which brings us to Section 3, understanding and overcoming drag. So, the crucial point here is that if thrust is the hero pushing us forward, drag is without a doubt the primary antagonist. And drag isn't just one simple thing. An aircraft actually experiences four highly specific categories of drag: parasite, form, induced, and interference. Let's break those down. First up, we've got parasite and form drag. Parasite drag is super interesting because it's not associated with creating lift at all. It strictly comes from the physical displacement of air by the aircraft and the turbulence that gets whipped up in the airstream. Just think of sticking your hand out the window of a moving car on the highway. Now, form drag is actually a specific piece of parasite drag, but it's generated purely by the overall physical shape or design of the aircraft itself. On the flip side, we have induced drag. This one is the inevitable, completely unavoidable consequence of an airfoil actually developing lift. You just can't have lift without creating induced drag along with it. And finally, there's interference drag. This comes from the intersection of different airstreams, like right where the wing meets the main fuselage, which creates these swirling, turbulent eddy currents that pull back on the plane. All right, let's head into our final part, Section 4, the anatomy of airfoils. Now we're looking at the actual specialized tools engineered to manage all these forces, the wings themselves. If you check out the airflow over a rectangular wing on the left and compare it to a tapered wing on the right, it's pretty amazing. You can clearly notice how the air behaves totally differently depending on the geometry it hits. The physical shape directly manipulates the air exactly how the designer wants it to. To put that into perspective, a rectangular wing planform is super common on smaller general aviation planes, simply because of its highly stable characteristics. On the other hand, a tapered wing is what you use for planes that are operating at high subsonic speeds. But Engineering is always a trade-off. While tapered wings are undeniably faster, they just don't have the desirable, safe stall characteristics that simple rectangular wings do. So, who actually figures out what these precise shapes should be? Well, that brings us to NACA, the National Advisory Committee for Aeronautics. They were the absolute pioneers here. They're the organization that fundamentally developed and cataloged specific airfoil shapes to optimize flight performance for different wings. And it really isn't just about drawing a nice curve on a piece of paper. The shape of a NACA airfoil is described using a series of highly specific digits. The parameters in these numerical codes can literally be entered into complex mathematical equations to precisely generate the cross-section of the airfoil. It lets engineers accurately calculate its aerodynamic properties before a single piece of metal is ever cut. Now, one really specialized shape out there is the inverted camber. This is where points of the lower camber actually curve so much they reach all the way up to the upper chord line. And here's a surprising fact. You almost never see this on a standard airplane wing. Inverted cambers are actually mostly used in the specific design of propellers and rotorcraft. But listen, all of these incredibly precise shapes have a breaking point. This is the absolute climax of that tug of war we talked about earlier. As the angle of attack, which is just the angle the wing meets the air, increases, your lift increases. But if that angle gets too steep, the smooth airflow abruptly and violently separates from the wing. When that happens, lift is completely destroyed. This is a very dangerous condition called a stall, and it's literally exactly what pilots spend hours training to prevent. So, to prevent that, and to keep the aircraft perfectly stable while managing the angle of attack, engineers rely on something called the aerodynamic center. Think of this as the ultimate balance point of the wing. It's a critical spot in the cross-section where the pitching moment remains practically constant, no matter how much the angle of attack changes. It gives designers a rock-solid focal point for all their stability calculations. Wow, we have covered some incredible ground today, from the basic tug-of-war of lift and weight to the pure mathematical precision of NACA airfoils, right up to the very real dangers of an aerodynamic stall. By understanding this complex dance, we really see that flight isn't magic at all. It's a beautifully calculated manipulation of nature. So, I'll leave you with this final thought. Knowing what you know now about aerodynamics and structural design, how do you view the manipulation of these four forces as we look toward the future of aviation? Thank you so much for joining me for this explainer, and keep looking up.